Hi, I'm Gary Gilliland, and today I'm going to talk to you about safety critical multicore for avionics. Um, I represent a company called DDC-I. We're a leading provider of safety critical software headquartered in Phoenix. Our primary market is safety critical avionics. That's kind of my background, the company background. But what we want to talk about really today is the idea of avionics going to multi-core platforms. There's a lot of reasons for that. One is, obviously the higher performance that's available. Also the gain in size, weight, and power to get that performance. The idea of having concurrent execution on multiple cores, and really just to get the latest technologies. It's very difficult to find a processor that doesn't have multi-core these days. So I put this picture up as a kind of an example architecture. It's an NXP architecture. It's one from their data sheets. You can see it has multiple A53 cores up here. But the more interesting part is the parts I've outlined in red here, where these are all shared components. So all these cores share the cache, share the coherency fabric, share the memory controller, the memory bus, like that. So this idea of sharing resources causes some challenges with multi-core, especially in the case of software and software applications. So you must figure out a way to deal with shared memory resources, such as last level cache, system buses, memory controllers, access to I/O that might be shared. None of the hardware is completely isolated for us in the scene. You also have this idea that the software can induce interference. So if your applications are not architected correctly, they could cause problems by trying to share the same resource at the same time. So you need to pay attention to how and when to use resources and develop your applications with care with that in mind. So to meet the challenges of multi-core, the certifying authorities in US, EASA, around the world came up with a guidance document called CAS 32A. There's also new documents in work that reference CAS 32A, but most of them have this concept of following a similar process as you do with DO 178, which is the process we use for software safety in aircraft. You have to determine what the planning is, so how many cores you're going to use, what the architecture looks like, how to manage the cores, and put together the planning documents and understand how you're going to deal with interference channels, how you're going to verify those interference channels, do something with error detection. So if something goes wrong, how you're going to deal with that, and report all this evidence. So that document, CAS 32, provides certain objectives, and the objectives are listed here. Some of them are for A, B, and C DALs, or design assurance levels. Some are just for A and B. So depending on which design assurance level your system is, you have to meet certain requirements of this document. As far as the authorities are concerned, you need to fill out these, basically respond to these objectives. This is kind of an example that we've done for several of our customers. It just explain how you're going to meet the objectives and what parts of the OS you might be using to do that. But, it's not just the application developer that has to work with this. The responsibility for a multi-core system is broad. It takes using system integrator, the hardware vendor, and the documentation they have to provide for the hardware and how it meets DO 254. And then the RTOS provider, what are they going to provide for you? How are they going to help you manage the multi-core processors? What kind of DO 178 evidence are they going to provide? And then the application developer can use that and provide that to the system integrator who has to put all this together and understand exactly how it works, how the cores work, how the applications work, and how the system can come together. So just as a kind of step-by-step, typically you'll find hardware, and this is just after the hardware is decided on, then you need a robust resource time and partition RTOS. We happen to provide one, but there are several out there. you need to define the interference channel. So looking at the hardware, some people also use third parties to help them understand interference channels and do that. So what's the cache like? Is it shared between cores? Is it grouped in bunches of cores? Or, there's various different architectures out there. How does it access memory? What I/O devices are available, and how do you access those devices? So those are kind of things where you define what the channels are, and then you specify the interference that might come from those channels and how you might eliminate or bound any of that interference. In the case here, I use what Deos features would give you the ability to limit that interference, but in general, what RTOS features would give you those features and those capabilities. So once you do that, you want to verify the correctness, and a lot of times what the interference is going to do to you is it's actually going to make the worst case execution time of your applications go up. So it's important to understand how you're going to verify the interference and what you're going to use to do that, either built-in worst case execution time like Deos has, or some third-party tool such as Rapida that will measure worst case execution time. You also might use Rapida's Rapidaemons that generate interference and see how that affects your application. So there's lots of different ways to do that. You also need to provide appropriate safety nets. So these are things that you've put in place so that if all your strategies for interference fail, the safety net will see that, will see that you've gone over some limitation or some boundary, and it'll give you control to be able to stop that application, restart that application, or basically handle it in whichever way your safety monitor wants. And then, of course, you have to document everything you've done. So from there, we look at interference channels in general. And through our research, what we've determined that the cache, especially that shared cache, is one of the biggest factors in interference in a system. The fact that these processes are sharing this cache and you have little control of that, something must be done, or you're not going to end up with a multi-core deterministic system. So just as an example of what I'm talking about here, if you look at a single core environment where, say, you have process 0, process 1, and those are in the CPU, they're running, they're sharing an L2 cache. Since you have very little control over where your code gets in memory, you have very little control of where that software gets in what cache line and that kind of thing. So it's very easy for an application to run a context switch to another application. He has to evict the previous data in order to fill a certain cache line in order for the P1 code to run, and vice versa. So you could end up overriding the same area of cache with two different applications very easily. And there's not a lot you can do in typical systems. Now, if you take that problem and you move it to a multi-core environment, now you've got that same thing going on multiple cores. So now you have core 1, and it's having misses and thrashing between its two applications. You have core 2, and it's having misses and thrashes between its. So you can see as you go to more and more cores and more applications, you're going to get a lot more opportunities for cache misses and cache flushes and refills, and really extending the worst case execution time of your applications depending on the configuration and the way the system's set up. Some hardware vendors provide a way that you can partition the cache to a core. So in those environments, you can make the problem a little less, but you still have the single core problem. So unless you plan on only running one application per core, the hardware partitioning of shared cache doesn't really help you a lot. Even in the days when we were doing safety critical software just on single core environments, there were things that were put in place to try to deal with this cache variability. Stuff like cache flushing, disabling cache, were very common approaches back then. And what would happen is that every context switch, the cert authority might make you flush cache, and then that way, when it refilled the cache and did everything was very consistent. That did make it consistent worst case execution time, but it does reduce performance. And if you take that to a multi-core environment and you flush cache, it's even worse because now you're flushing and refilling all these caches, and the caches are getting larger and larger as you have multiple cores. So it takes more time. The other option was disabling of cache, and that one causes a huge performance penalty because the modern day processors are just not designed to operate without cache. And so they operate quite a bit slower, and you're not allowing them to operate in the way they're intended to operate. So then there was several cache partitioning schemes that have come up. Some give user level locking of applications. So you put an application, lock it into a certain area of cache. We have with Deos, we have our own cache partitioning scheme that's patented. And the cache locking architecture works. It's not very portable, but it works. Although some of the newer ARM processors don't even give you user level cache locking. So that kind of makes that one a little more difficult going forward, at least in the future. From a Deos perspective, we provide features to address CAS32A, shown here: memory pooling, cache partitioning, safe nets, and safe scheduling. Various different RTOSes will provide different approaches to this. They may work with the memory, may do hardware partitioning, may do work with the performance monitors and the hardware. So you just have to talk to your RTOS vendor to see what those are. But for Deos, these are the ones we use. And like I said before, the Deos cache partitioning scheme is patented, and we actually partition the cache per application. So that means that each application has its own separate area of cache. It's portable. It works across all of the architectures we support: x86, PowerPC, and ARM. And it's processor agnostic, so it doesn't require any user level or actually any cache locking or cache instructions to be there. It's also been verified even in our single core environment back to 2015 was the first time it was verified. So what would that look like? So this picture is kind of an idea of using the concept of cache partitioning. You could have 5 applications on 2 different cores and have 5 areas of shared cache. And the way to think of this is, if you understand how cache works, cache is loaded by address. And the way that Deos works is that memory pages, 4K pages, are allocated to an application. So basically what we've done is, through our configuration, you can set up certain memory pages to be associated with an application. Those memory pages have the same lower address bits, which allows them to be mapped into a certain area of cache. And that's how it's separated. There's white papers available on our website that go into the gory details of how this works, but in general, that's the idea there. But it's all done through XML configuration. It only takes 3 parameters, so it's pretty simple. It's easy to reconfigure and test and try things out. So we came up with this idea. We put it out to some of our tier 1 avionics vendors and had them test this. And so this particular test was a flight control application, and the vendor ran 3 different tests. One where they had basically L2 was not partitioned, so any application could use any area of cache. And then they turned L2 off, and then they did the cache partitioning as described by the operating system. So the first test is the gray band. So you can see at the bottom of the gray band that would represent the best case execution time was in the 30 microsecond range. And the top of the gray band would be the worst case execution time, which is in the order of 100 microseconds. So over 1,600 frames of running this application, what they found is basically the application varied between 30 and 100 microseconds for execution time. That's a pretty wide range of execution time. So the next thing they did was turn the cache off. So that red band represents what was seen when they did that. And you can tell that the variability went down significantly, but the performance was impacted quite a bit. So now the best case is a little over 60 microseconds, and the worst case is 80, but the variation is only about 20 microseconds, which is better from one perspective, but you're losing a lot of performance of your CPU. So then the third test was the green band, and they implemented the cache partitioning. And you can see the green band's variability is very small. It's from roughly a little over 30 to 40. And the variability then is about less than 10 microseconds. The best case is a little less, and the worst case is significantly less. So you can look at this and see that, cache partitioning provided a better worst case execution time. It provided less variability. And if you think about it, everything from 40 up to 100 now is free CPU time for you to use with other applications. So that's improvement in performance and capability of the processor you're using. So this was kind of our aha moment that we were on the right track with dealing with cache and how the system should work. Another aspect, though, of dealing with interference besides cache is the idea of scheduling your applications. So, there are options for different scheduling mechanisms in different RTOSes. The way Deos provides this capability is this concept of a window of time. So the dotted lines represent windows of time, and in that window of time, you schedule applications on different cores. Now, if you want to continue the same applications in the next window of time, you can. It's flexible in that way. You can have as many of these windows as you want. We show 4. You could have 1. You could have 1,000. There's no real limit there. But what this does for you is within the dotted line windows, within those windows of time, is what you have to do your timing analysis for what's executing on all the cores and what interference would be in there. So what resources are being shared and those kind of things, and how to deal with that. So it shrinks the problem of that analysis down to a window of time. And that's the point. You want it to bound and control and minimize any cross-core contention that might exist in those windows of time. We provide different APIs, so you can have 653 applications, you can have POSIX applications, RMA applications. You get to pick which scheduler you want to run in which window on what core. In that model, and we'll use that model as an example, but this would all be true basically for any model you choose, any RTOS you choose, is that as a system integrator, you're going to have to look at all the applications that are required for the system. You have to determine what are the resource requirements for each one of those, determine the interference patterns, look at the applications from are they memory intensive, are they CPU intensive, are they IO intensive, what IO do they use? And basically with that information, then you can say, I want apps that can benefit from parallel processing. So that's, part of one of the big reasons you're going to multi-core is the idea that you could actually run simultaneous applications and get more work done in a smaller amount of time. So you want to look at those and see what those applications are and schedule those in the same time space. And then applications that, say, share a certain interface, if they're using the same IO device, you want to separate those in time so that they don't interfere with each other. And then applications that create little interference, don't share, the IO or such, those could be scheduled wherever they fit best in the time pattern. And like I say, there's multiple ways that RTOS vendors do this. In our windows of time, this model fits very easily. It's easier to see where you can put things and how they work. CAS32 also requires that you do something with safety nets. And if you remember from earlier, safety nets are really, you've decided what you're going to do, you've tested it, you've proved how it's going to work. Safety nets are, what if something happens in flight? How are you going to deal with it then? And so typically the only way you're going to know is by using a capability in the hardware. And most of the hardware that we run on these days has something in the way of a performance monitor or something like that, that has counters that can count last level cache misses, can count bus traffic, different hardware events that happen. And so basically the idea is you come up with a normalized value for these things in your system. And if one of those values is exceeded while you're running, then you can be informed of that via an interrupt or something. And then you can have your safety monitor look at that, how it happened, if maybe what you want to do is restart the application. Maybe you just want to stop that application from being scheduled for a few major frames. Who knows? It's up to you. It's just giving you the information that you need to make the decisions about your application and how it would work if one of these things should happen. That's kind of about Multicore and CAS32A and how we would do it. These are just a few highlights from Deos. I'm not going to spend a lot of time on there. I put them in here too, so you'd understand where I'm coming from with our product. Deos is flying in tens of thousands of aircraft, millions of flight hours. If you've ever flown on an airplane, you've probably flown on an airplane running Deos. It's in a lot of different types of applications. Very high performance, multi-core, and we have all the tooling necessary to meet all these what you need to do for CAS32A and for DL178, coverage tools, worst case execution, and so on. We support most of the common multi-core processors, the latest Intel Tiger Lake, PowerPCs all the way up, and ARM is probably one of the most popular. So lots of A53s, A72s on different hardware platforms. And like I said, provide the tools. We use Eclipse. We have a development environment using GCC, Ada, give you mixed language debugging, give you a simulation environment to run before you have your real hardware, as well as reference boards to run on, and then the tools to use during verification. One of my slides showed that the kernel actually keeps track of worst case execution time and reports you that through our status monitor and graphical information tools. So lots of different things. We provide a structural coverage tool, but we also work with the guys out there with LDRA or with their competitor that I won't mention. And we also have configuration tools all based on XML. So every application has that, and to help with the timing analysis and to determine whether the system is actually schedulable or not. So in summary, Multicore provides some pretty significant challenges. Here at DDC-I, Deos addresses those challenges. We have features implemented in software that significantly reduce the problems with dealing with those, including cache partitioning, memory pool, safe scheduling, and then providing you the tools necessary to help you develop your multi-core application and ease the integration of those things, as well as integrated with third-party tools needed for some of this in the multi-core environment. So I want to thank you for listening to my presentation.